All right. So can somebody tell me what it means to be chiral? John says 4 different groups. So yeah, that's your non-superposable. Those are definitely your telltale signs. Your 4 different groups is definitely the easiest that you can come across, because the superposable, the mirror images and this and that, I would rather not do the mental gymnastics. So he could ask you, which one of these is chiral? To me, that would be too simple. So I would think he's going to ask you which one is capable of existing as an enantiomer. And it means the same thing. He could ask you which one's capable of existing as that, or which one is capable or can rotate light. It all just means which one of them is chiral. All right, and so what I would do is just start by drawing it out. So looking at this, here is our 1,3-dichlorobutane. So based on this structure, do you see any chiral centers?
Yes.
Someone says yes, Leah says no. All right, so here on this carbon on the left, you have 2 other hydrogens, chlorine, and another CH2. So again, like John said, the 4 different groups, these 2 hydrogens are the same thing. They're considered 2 of the same groups, so that is not a chiral center. Same thing with this carbon here. It's 2 of the same groups because it has 2 hydrogens on it. This wouldn't be it either because of the 3 different hydrogens, so this one is our possibility, right? So on this end, we have a CH3. On this end, we have a CH2. Here we have a chlorine, and there's an implied hydrogen. Those are 4 different groups, right? Thus, here is your chiral center. Any questions on that? All right, moving along. Again, I'm just going to draw these ones out for you guys. All right, so based on this molecule, based on this drawing, do you guys see a chiral center? Daniela says no. I see salmon free. Carrie says yes. So there's only really one possibility, right? Here. And so based on that, whenever there's a ring, you'd have to go around the ring looking for something that stands out compared to the other side. So of course we have a bromine going along. Right? So going along here, we have a CH. Here's a CH. And here's a CH2. There's nothing going around the ring. There's no other carbons to compare. So based on that, everything is the same. Thus, there's no 4 different groups coming off of that carbon, and therefore it's achiral. All right. Someone said that they think that the exam is going to have some bigger molecules. You're probably right. So that's why I wanted to throw a bicyclic in this. And I'll draw it, which I think would look like this. I'm just drawing this one in 2D. All right, so this one's pretty almost the same exact thing to the previous one, right? So looking at this carbon, looking at this carbon, do you guys see 4 different groups coming off of that and or going around the ring? No, right? So when there's not even any chiral centers, it would not be chiral at all. Allison, no, not necessarily. That's when you have a ring, there is symmetry. And one thing you'd have to look at is whether or not you have a plane of symmetry and 2 chiral centers cancel each other out. So we'll get to that, which in that case would be a meso compound. This one is, again, relatively simple, but it's really, you just simply apply the concept that you know to all of these molecules. So the only possibility we're looking at is on this one. And yep, John is right, it's achiral. It's here. You have the same thing coming off of it. Here's a CH2. Here's a CH2. Here's a CH2. And even extending off, going to the other carbons, it's the same thing. Here's CH3, CH3, CH3. So you have a massive amount of the same exact groups coming off of that carbon, thus achiral. All right. So that's you know, it's not going to get too much complicated. Beyond that, it's not going to get much more complicated. If you know your rules of thumb, you know what you're looking for, then you can just apply that to almost all your other molecules. Gustavo, again, if it were a ring, like here we have a CH2, here we have a CH2, but let's say, for example, this carbon has the bromine coming off of it, right? Now this side of the molecule is different from this side of the molecule, right? Because if you meet 2 groups out of the same thing, you have to continue along to see if there's something that makes that side different. In this case, it would be this bromine compared to this methyl. So hopefully that answers your question. Yep. So just to intro, this is actually from a prior SI. Priorities. So these are already designated your priority. But can somebody tell me what you're looking for when it comes to priority? How would you rank them? Yeah. So not even just the biggest one, but the simplest way you could also look at it is atomic number. But we'll get to that soon because these are already designated. And so there's a rule of thumb that we like to use. Does anybody know it? So there's this thing, right? Instead of having to build a model kit and go through the mental, Jermaine gets a little twinkle in his eyes. He's like, oh, there's a little man looking down this bond. No, I'm not going to do that. So there's this thing where you ignore what's in the back. Yep, you cover what's dashed, right? So you act like that's not even there. And then you find your rotation. In this case, 1, 3, 4. Right now, that would be S, right? Is what we covered priority 1 or 3? No. Therefore, we keep the rotation that we got. That's it. So with this bottom one, let's cover what's dashed or in the back. Find our rotation. Here, it's S, but what we covered was a 1 or a 3. So we flip what we got. It's really R. Make sense? Yeah, so in this one, we cover what's in the back, which would be 3. 1, 2, 4. What we have now is R, but what we ignored was a 1 or a 3. So it's really S. Simple as that. All right, and so because of that trick, it takes care of having to flip it and to find the position of where you would have the 4 in the back. That takes care of that. So that's what I've always used. So to go on to bigger and better examples. So the one on the left. So the one on the left, let's just start from the right. All right, so here, this isn't a chiral center, but this one is, right? So coming from directly from that carbon, which one would be your number 1 priority?
The CL?
Yep. And because that would be, I always like to find my first and last. So can somebody tell me what our 4th priority would be?
The H that is hidden?
And in this case, it would be dashed. So our 4th priority is that hydrogen dashed. All right. So now we're comparing this carbon on the left and this carbon on the right. So you would have to look at, since they're both carbons, you would have to look at what those carbons are then attached to, right? This carbon is attached to hydrogens. This carbon is attached to a bromine. What takes a higher priority? The one attached to the Br. 2 and 3, right? So we use that rule of thumb. Cover what's in the back, which would be that dashed. 1, 2, 3. What do we have? S, right? Is what we covered a 1 or a 3? No. So it's S. So let me clean this up a little. So looking at the next carbon, which would be this one. Which one would be our highest priority? The Br, because again, directly attached. And like the other one, we have an implied hydrogen, which would be 4. All right, so looking at the left side and the right side, which one would be the higher priority? So 2 and 3, right? We cover what's in the back, which would be 4. Right now we have S. I mean, yeah, we have S. Do we have to flip it? No. So that's that. So a rule of thumb that if you can catch on to this trend, if what you have in the back is a 2 or 4, then you keep what you got. But this one with the fluorine, I believe we would have to flip. All right, so let's do it. Looking at this one, you guys are doing pretty good. So this one is our first priority. We have a hydrogen, implied hydrogen, which would be wedged, right? And that would be our 4th priority. All right, so which one is our 2nd priority? Daniela says the 2nd one with the BR. Yep. And this would be 3. So cover what's in the back. Remember, your 4th priority isn't always going to be in the back. Same thing with 1 or 3. It doesn't matter which one is in the back initially, right? So you find your priorities, then it doesn't matter which priority it is. If it's in the back, you ignore it for now. So you ignore what's dashed. In this case, that would be 1. So 2, 3, 4. Right now, that's R. Do we flip it?
No. Oh, yes, yes, yes.
So what we covered was a 1 or 3, so we do flip. All right. So seems like you guys are doing pretty well on that molecule. Do you want to do that last one, or do you want to go to one of these other molecules? Someone break that tie in the chat. Someone said the last carbon. Someone said another molecule. Someone break that tie.
Can we do the ring one, please?
Yep. Which ring one? The one with
like the one to the right with the H2N.
So right now we're really only looking at the center one. Right? That's really the only possibility. So which one would be our first? The CL. All right. Now we're comparing this nitrogen, this carbon, and this carbon, right? So which one would be our last priority? Well, what comes first? Chlorine, the carbon or the nitrogen? The N. So that would be 2nd. All right, so just comparing this ring and this ring, everything is the same except one of these carbons has a chlorine coming off of it. So which one would be our next priority? Yep, the ring with the Cl will be our 3rd. 3, thus 4. All right, so cover what's in the back, which in this case is 2. All right, so again, go in order. 1, 3, 4. Wow. 1, 3, 4. It's S. Do we have to flip? No. So it's S. Now, a lot of people try to overthink the clockwise and counterclockwise. I'm pretty sure all of us have driven something with the steering wheel before. If you're turning the car to the right or whatever you're driving, if you're turning it to the right, it's R. Right for R. All right? Don't overthink it. All right, so that third one is just like that first one. So how about the last ring? So we're looking at 2, right? So let's just look at this one, right? What would be our first priority? Yeah, so that would be our first. And we have a implied hydrogen. Yeah, Carrie's getting all Latin on this. Actually took Latin. Our implied hydrogen would be our fourth. Now, what would be our second?
The C to the right,
Why?
because it has the S connected to it, attached to it,
Compared to the left, which has what?
which has 2 H's only.
Yeah, so 2, 3. All right, so we cover what's in the back. 2, 3. All right. So which way are we turning the wheel? R or right? Do we have to flip it? No. So that carbon, that chiral center is R. All right. So let me clean this up to get to that other one. So looking at this other one, like the last one, our number 1 priority is this sulfur. Now this one's a little tricky, right? So what would be our next priority? So we're looking at a methyl here, a carbon attached to another carbon, a carbon attached to an S. So what in ranking for what would be our second highest? Yeah, the carbon with the S. And what would be third? Someone says the CH2, why? Yep, it's again attached to another C, which is higher than attached to hydrogens. So this would be 3, and this would be 4. All right, so cover what's in the back. 1, 2, 3. And this one would be S. Do we have to flip it? No, because what we covered wasn't a 1 or a 3. So that's it. All right. Does anybody have questions, comments, concerns on that rationale? All right. Yeah. So again, I'm just going to draw this for you guys. This is our staple here, our 2,2,1 heptane. All right, and you have 2 chlorines coming off of the same carbon. So how many chiral centers does it contain? I believe somebody in the chat earlier nailed it. So it's definitely not the one with the chlorines, right? That's a given. The bridgeheads. And it would be, I get how it's counterintuitive because this is a CH2 and this is a CH2. But going around the ring, they're different, right? If you go this way, here's a CH2, here's a carbon attached to some chlorines. Here's a CH2, and here's a carbon attached to, it's just another CH2, right? So in this case, these two bridgeheads are your chiral centers. And now if I were to ask you, how many possible, what's your predicted amount of stereoisomers? There's a rule that we would use, right? 2n. N is how many chiral centers that we found. So 2 to the power of 2 is 4. So if he were to just give you a molecule and ask you what's your maximum number of predicted stereoisomers, you would simply find how many chiral centers there are and do the rule, right? So meso, gotta love them.
Michael, can I ask a quick question?
Yeah.
Is that considered cis or trans?
So we actually didn't designate if these chlorines are pointing in opposite directions, really. And in this case, if this chlorine is attached, okay, so I'll say here, this chlorine is pointing down, right? And we know dashed is down. So if it's that one, if that one is dashed, and let's say this one has a chlorine here, which is pointing in a downward direction as well, that would indicate in 2D that was dashed formally. So if they were both, if they used to both be dashed and thus both pointing in a downward position, you would say it's cis.
Okay, cool.
But that's not necessarily something you would have to worry about for this type of problem.
Okay. Thank you.
So here you're not even given a name. You're just given the Newman projections and it's asking you which one's meso. So does anybody know what they're looking for when it comes to meso?
So isn't it when it has chiral centers, it has symmetry, but it's achiral?
Yeah, so there are chiral centers. Somebody also got it. There's also plane of symmetry. And what happens is that you have a plane of symmetry and those two chiral centers, they cancel each other out. Overall, a chiral molecule. So we'll do that right now. So one thing, this is actually, I see this every semester on a quiz. This came up every semester on a quiz almost identically. So what I would do is I would rotate, right? If you were to rotate the front carbon, let's say the one on the right, if you were to rotate this front carbon 160 degrees, right? Your CLs, everything, it would be eclipsed, right? It would become eclipsed. Does everybody see that? If I were to rotate the front carbon 160 degrees, it would become eclipsed because things are becoming in line with each other, right? So the CLs are in line, but the CH3 and the H aren't mirrors, right? Only the CL and only the CLs are mirroring each other. The whole thing has to be a mirror, not just one group. So if you're given a Newman, rotate to find it, rotate it, and redraw it if you want, rotate it, make it eclipsed, and see if everything is a mirror. And in this case, it would be A. And here, I'm gonna actually draw it. So if you were to keep the back carbon the same and only rotate the front carbon 180 degrees, keeping the back carbon. So your back carbon is this. And if you were to rotate the front carbon 180 degrees, you would see that the CL is aligned. The H is aligned. And the methyls align. So right now, this whole entire thing is a mirror, right? Down its plane of symmetry, everything is the same, right? Do you guys see that? All right, so thus, in comparison to the others, this one is your meso. And in order to draw it in 2D, just to give an example, because someone brought up cis or trans, if you had something like this, where's the plane of symmetry?
Like between the two CLs, horizontally?
Yep. And if you were to do the RNS for this, I didn't even do it, but just an example, I know they would be different. One of these is R and one of these is S. So let's just say this one is R and this one is S. If you have a plane of symmetry like this and your two chiral carbons oppose each other with their R and S, then it's overall achiral and thus a meso compound. So does that clear up some things? All right. Let's see. All right, so relationships. Just to make it easier on you guys, you guys so badly overthink enantiomers and diastereomers. You have to have two chiral carbons in order to be a diastereomer. First and foremost, right? So would either of these two examples be a diastereomer of each other? No. So you already know that's out of the question, right? So if you're given something like this, on the exam he could give you, compare these two, what are they? And you know that right now that they're not diastereomers. So right now we're looking if they're enantiomers or the same, right? So can somebody tell me what they think it would be? Samuel says the same. Does anybody else concur? Yeah, so if you were to just rotate this if you were to just keep everything on the plane and just rotate this 180 degrees, you would get this. RNS stays the same, nothing else changes their connectivity or dashes and wedges, it's just rotated, right? So this would be the same, they'd be the same molecule. All right, so this one is a little bit different. You know it's not diastereomers, it's not the same because you see that here you changed you changed the geometry and what is located in space. Right? And if you are doing that, you're creating different forms of the molecule, right? Thus, these two would be considered enantiomers. But you're less likely to get that kind, on exam. You're more likely to get something more like these on the exam, something that has more than one chiral carbon, which you just kind of split it in half. So if you were to given this, don't even worry about mirror images or superposable or this and that. Worry about that with fucking, I don't know, Orion. But on the exam, you're not going to have time to do that. RNS it. So RNS the hell out of these. So so you would just split it in half, right? On the left side, what's your first priority? You know, you have your BR. What's your lowest? Your H. And what's your second? Right here, you have a C that's bonded to hydrogens. Here you have a C that's bonded to all this other shit. What's higher? This, right? And here you have your third. Cover up what's in the back. In this case, that's 1. So 2, 3, 4. Right now we have R. But what we covered was a 1 or a 3. So that front carbon is really S. And you would do the same thing for the back carbon, all right? You do the same thing for the back carbon. So for example, I'm not gonna run through this because I don't want to run out of time, but let's just say this one is SS, right? And let's just say this one is SR. Now there's a thing we like to say, all right? If they are enantiomers, all the chiral carbons have to be opposite in RNS. So in comparison, this molecule has SS, this molecule has SR. Are all of the stereoisomers changed? No. So it's a diastereomer. If you have all of them changed, R, then it would be an enantiomer. Right? And it doesn't matter, you could have 4 carbons for all they care, right? If you're comparing, let's just say a molecule that has RS versus another molecule that has SSS, are all of the stereoisomers in comparison changed? No. So what would it be? Diastereomer, right? And let's just make them all changed, just some giggles. Now it would be considered an enantiomer because all the chiral centers flipped configuration. So that should definitely speed up the process in the exam. Just RNS it, all right? Any questions on that? So we simply got the dash and wedges. So I have no idea kind of what you're asking, John. And Kavi, what's the last one again? What do you mean? All right, so again, this one I would have to, if you guys actually want to.
I worked it out, it is SS. Maybe someone can back me up on that.
Yeah, I'll just do it anyways. So F is your first, H is your fourth, this would be your second, this would be your third. We cover what's in the back. 2, 3, 4. Right now it's R, but what we covered was a wedge, was a 1 or a 3, so we flip. So it's, yeah, whoever said that was right. So Kavi, yeah, I was just throwing out a random example. It's not on the page. I was just saying arbitrarily, for example, if you were given a molecule and you did the RNS, that's key, right? Do your RNS. It makes it very simple for you guys. You don't have to go through worrying about, you know, symmetry, superposable, whatever it may be. Just do the RNS. So if you have a molecule that's, say, RS, if the other molecules, chiral centers, all have the RNS flipped, if all of the carbons are flipped, then it's an enantiomer. If not all, but some change their RNS, like in this example, if only 2 of them changed. So not all of them, but some of them changed their RNS from one molecule to another, then it would be a diastereomer. No problem. The question is for diastereomers, can't we just change the wedges and dashes? So the thing is that you're going to be given the wedges and dashes, right? So yeah, I would be careful because you can, if you change the wedges and dashes, not only are you changing the geometry, but he could also change what is wedges and dashes, and thus you would also change the possible direction. Without doing the RNS, you don't really know what direction it's rotating. So that's why I would do the RNS. So yep, that's what I was taught for all these in comparisons. RNS it, right? So Fischer projections, all right? So this is just a wedge and dash on the plane, right? So has anybody touched on these before? Fischer projection. Yeah, so what's on an arm, right? Just like a scarecrow, because spooky season. What's on an arm is wedged. And what is on a head or the feet of the scarecrow is dashed. So you do your priority, right? So this would be 1, this would be 4, and like the others, this would be 2, 3, right? So cover what's actually, because of this trick, you don't even have to worry about covering or this and that. Do your priority, find your rotation. So 1, 2, 3, 4. What is this right now? What rotation? RS. R. Is our lowest priority on an arm? Yes, so we flip. Simple as that. For Fischer projections, You do your rotation. Don't worry about covering up. Just do 1, 2, 3, 4. And if your lowest priority is on an arm, you flip what you got. All right? In that case, once you find your RNS, then you'd be able to, figure out whether they're diastereomer or enantiomers. Any questions, comments, concerns? All right, so this was a former quiz question. Which one is S-butanol? So obviously they're both 2-butanol, but which one of them is S? So let me know what you think. Someone says A. That was relatively quick. Does anybody else concur? All right, so someone else said A. All right, so going through it, since everybody's saying A, I'll start with B. On this one, what's our first priority? The O. And like I was saying before, it doesn't matter what is wedged or dashed yet, right? So like we see in this example, we haven't seen an H on the plane itself. We've always seen it wedged or dashed. So in this case, your fourth priority isn't a wedge or dash. So again, it doesn't matter yet, all right? So you just find your priority. So what's your second priority? That methyl or the other? Daniela says the other. Anybody else agree, disagree? All right, so it is the other. Do you guys understand why? John says less H's. But really, here you have 3 hydrogens, which is really, it adds up to an atomic number or atomic mass of 3. Here you have 2 hydrogens and an atomic number. So it just adds up to more. You have that extra carbon that is bonded to. So in this case, we cover up what's in the back. So 2, 3, 4. Right now it is S. Do we flip it? Yes. So it's R. So yes, you guys were correct in saying that the answer is A. So is there any questions, comments, concerns on how we got that? All right, so Daniela says neither of them. So let's do A. And it's the same atoms, same groups. So this would be 1, this would be 4. This is of a higher priority than the methyl. All right, so cover what's in the back. One, 2, 4. What is this right now? R. Do we flip it? But it's really S. All right, no problem. And this one, you may not even see it on the exam, but I'll just give it to you guys in case he throws it at you on a quiz. It's A. All right, so if you have I know it's confusing It really comes down to the technical definitions of, and it comes down to orbitals as well. So this molecule, A, is called an alene. You're like going to see it once maybe. So they have this double bond sequence, and the pi bonds, if you were to draw out the orbitals, the pi bonds, yeah, if you have to go, so yeah. The pi bonds end up being perpendicular to each other, and the geometry of the pi bonds attached to the carbons lie in perpendicular planes. And because of that, the allenes with the different substituents on the ends carbons are chiral. And they show cis-trans isomerism. So you don't have to really know that complicated reason. Just know that in comparison, A to B, A is what is chiral, right? Just in case he throws that out. So, any questions, comments, concerns before we end things? No? All right. So, go back to this. Screenshot who's here. All right, so since that is all I have for you guys, I actually have to go. I can't stay back because I'm covering for Emily at noon as well. So hopefully that cleared up a lot of things, because I know chapter 5 can be pretty confusing, but it's a matter of practicing, right? We gave you all these tips and tricks so you can really make it as easy or as hard as you want. So remember your tips and tricks and you can apply them, all right? So with that, send you guys off.